Y7, current and resistance. So current consists of flow of tiny charges, usually electrons, drifting electrons. Here you can see elementary charged particles that constructs a current. Suppose that we have n such elementary charges of each charge q contained in volume V. So number divided by volume is called the number density. And each particle, it looks complicated, randomly moving, but on the average, we assume they are moving with identical velocity v. Current density is defined by the density of a charge multiplied by the velocity. It is very, very similar to the mass current flow that we learned in the previous semester when we studied the continuity equation of fluid dynamics. That rho is a charge per unit volume. So rho is a charge per unit volume. And each charge has a charge q, and there are n such particles in volume V. Therefore, it is a small n multiplied by q. Therefore, current density is expressed as a product of the number density, elementary charge, multiplied by the average velocity of those particles. So current density is rho v, and eventually rho is expressed in terms of the product n times q. The unit of the current density is charge per time per cross-sectional area. So that is charge per time, that is a current ampere, but divided by the area. Okay. So current, the charge per unit time passing through a cross-sectional area d sigma, and d sigma has a magnitude d sigma and the unit vector multiplied to this scalar. So we have a direction of the infinitesimal cross-sectional area, and we have current density J. So if I take the scalar product with these two, J dot d sigma represent the current. So this is a trivial example. I think you can follow what's going on in here. Uniform current of identical charged particles of each charge q with the number density small n is n over v is moving with a constant velocity small v. V is the parallel pipe whose two opposite faces are S1 and S2. S1 and S2. Both with the direction parallel to V. Both of them has the vector direction that is parallel to the velocity. This is at t, and this figure shows the situation at t plus dt. because every charge is moving with velocity v, there is a displacement by dx equals v times dt. This is the displacement of charge that used to be there at t, and this is t plus dt. During this infinitesimal time interval, the net charge passing through the surface S2 can be computed as the capital Q, and we have cross-sectional area. S2's cross-sectional area is a vector that is a times, let's say it is n hat. This is n hat. Then you will find cross-sectional area A, and this is the dx, that is a v dt, and this volume is dv, and this v dv is a dx, volume element. So volume element multiplied by density rho is nq. So density times the volume, that is the charge. Okay, let's rewrite this. Dx equals v dt. And we pull out this dt in here and combine this v with this. Okay, nqv. What's that? That is a current density. So current density multiplied by the cross-sectional area. This cross-sectional area J, so this is J dot A, right? J dot A dt. This J dot A can be expressed as an integral over this surface. Because it is constant, we were able to write in this way. However, in case every velocity may vary, therefore, we can express in terms of integral, dividing the surface into tiny pieces and sum them all. This is the integral of j dot d sigma multiplied by dt. We divide both sides by dt, then what we have is a dq over dt equals integral j dot d sigma integrated over some surface. Okay, that's the reason why we can write current I as a scalar product of current density multiplied by d sigma. What we have done in here is extend this tiny piece as a finite surface, then arbitrary surface can be considered to find out the current passing through this surface. All right, and then we next consider divergence theorem. Divergence theorem is divergence J volume integral is always identical. This is identity. This is always equal to this, identical to the surface integral. There is a volume and there is a closed surface. That is the boundary of this volume. Over this closed surface, we can evaluate the j dot d sigma. J dot d sigma is the current passing through the closed surface. Okay, this integral is always 0 if divergence J equals 0. Divergence J equals 0 means sometimes simplest case J equals constant. If J equals constant, that means this flow is uniform. So as time goes by delta t, this amount of charge has been emitted from this space volume V. However, because the same flow is coming in from the left, the missing contents of the charge is refilled from the left. That means current is uniformly flowing, so the charge distribution inside this volume, regardless of the flows of these charges, amount of charging contained inside the box is the same. This is not true if the flow coming in is bigger than the flow coming out. It is only the case when the flow coming in is the same as the flow coming out. In that case, this amount is always 0. That means we know this box consists of 6 faces, and these 4 faces, this side is closed, and this is out, and this is in. Amount of coming in is the same as amount of coming out, then this surface integral is, you know, this surface is toward outside, and this surface toward outside, and the same flow comes in, comes out. This amount is lost from this box, but this amount is gained inside the box. But this flow, as far as the flux is concerned, it is a positive flux. And this is a negative. Cosine theta is a -1, cosine theta equals +1. Negative flux. So sum of all fluxes passing through this closed surface is 0. Therefore, the amount of charge inside is always time independent. That is the continuity equation. Anyway, the current I passing through an open surface. This is an open surface, and there is a volume, and the surrounding surface is always closed. Here I missed something. This is the closed surface, so I have to put the circle on the integral. Okay, and this is the open surface. In here, S1 and S2 has the same vector. The directions are the same, so these are the same. N is the same. If I choose the direction from inside to outside, they are opposite. The charge passing through the S1 during this time interval. Where is S1? This is S1. That is expressed as a density multiplied by volume. But that volume is expressed as a current density multiplied by the cross-sectional area multiplied by time. Next, uniformly distributed identical particles with number density n. Here, this distribution is flowing upward. And their cylinder. Cylinder has a symmetry axis that has an angle with respect to the z-axis, and the flow is parallel to the z-axis. and this flow is uniform. Okay, the direction of this n vector that is perpendicular to the upper lid of this cylinder can be represented by this polar coordinates. Oh, I have noticed the errors. This is E1, this is E2, this is E3. That is right. We define the closed surface as that is the boundary of this cylinder, that is the boundary of the cylinder V. Find the full statement. Current density is a constant. Yes, J equals rho V, and the rho in here, that is N Q, that is constant, and V is also constant. So this is constant vector. Divergence J is exactly 0 everywhere. If divergence J equals 0, this volume integral must vanish. And according to divergence theorem, this is the surface integral. This surface integral, closed surface integral. Closed surface integral. We should put this circle. It is 0. That's right. And then time derivative of charge q. Yeah, let's see. This one, that is the same. And according to this one represents the amount of charge per unit time passing through the closed surface from inside to outside, right? Because current flows out of this volume. So if the net charge dq has been emitted from this volume per dt, what is the change in charge inside this volume? Because the electric charge is conserved. Once delta Q is emitted from this volume has lost the charge by minus delta Q. Therefore, continuity equation states that if the charge flow comes out of a volume, oh, this is not circle. This is a so volume integral in B should be corrected. So charge inside this volume must decrease. This negative sign indicates the decrease of the decreasing behavior of the charge inside the volume. However, we know this integral is because divergence is 0, this integral is 0. If left-hand side is 0, time derivative of net charge inside is 0. That means charge Q contained inside this cylinder is independent of time. So it is invariant. Invariant means it is not a function of time. It is a constant. The net current passing the upper lid is not a closed one, but an open one. We have a current density J, that is J is rho V and E3 hat, E3 hat in this direction. And we have lid whose area, cross-sectional area, is a pi r squared. However, its normal direction is n hat, and we have velocity of this current has E3 direction. Because this is area and current density scalar product, we need to consider the n hat dot E3 hat, because the n hat is in this form, and this one is 1 and 2. N hat dot E3 hat should be cosine theta, this one, because E1, E2, they are orthogonal to E3 hat. So we have to consider the cosine theta coming out of the directional cosine between the two unit vectors. The current passing the round surface of the cylinder is 0. Why? We have 3 pieces of surfaces, right? This amount is this current passing this surface. So it is coming out from this lower lip, the same amount, because direction is the same. However, it's coming in. And this amount must be the same. What happens to this? We know the sum of everything must be 0. Therefore, even though it looks very complicated to evaluate, I don't ask you to find out this stupid integral. Your clever way to find out the integral is it is a 0, because the sum of 3 is a 0, and these two cancels. What's remaining in the middle is also 0, because the sum of everything is 0. Number 5, uniform current of the same problem. The current density J of the red particle is the same. The two different things is a positively charged particle and this a negatively charged particle. Okay, the same current density can be achieved with the Q and V, and this is true if we flip the sign of both the charge and velocity. So this is an example of current when they define Benjamin Franklin defined the charge sign to be positive. However, the current flow is not due mainly. In some cases, a positive charge can move. However, mostly it is a drifting electron. Now we know the electrons are negatively charged. However, long time ago, when they constructed the electromagnetism, they didn't notice what charge is moving actually, and that's by accident that they have a wrong sign on it. So electron is the fundamental particle that carries the charge. Unfortunately, we have an opposite direction, an opposite charge. However, we can correct that mistake by flipping the sign twice. So the theory for the positive charge going forward is identical to the theory of a negatively charged particle moving backward. Okay, so we are still happy with that wrong theory to describe the actual fact. Current is defined along the direction along which positive charge carriers move. Actual charge carriers are mostly conduction electrons that are negatively charged. Current is opposite to the flow of conduction electrons. Consider flow of identical charged particles that enter S minus. It's a kind of funnel, and it passes through this side. This is a wider area, the smaller cross-sectional area. We remember, if it is a narrow, the flow comes in fast. If it is a wide, the flow comes out slowly. Anyway, we are still working on the situation divergence J equals 0. Divergence J equals 0, then we can consider a closed surface of this funnel, and surface integral over the closed surface must vanish because of divergence equals 0. In a similar manner, we expect that amount of flow coming in must be the same as amount of flow comes out. Because the cross-sectional area is wider than this one, the velocity of the charge flow in here must be smaller than that on the left-hand side. This is an interesting question, but because the answers are all given in here, let me pass this problem. Next one is actually once electric field is given, apply, then charged particle begins to accelerate. If it is inside of in a vacuum, they will accelerate and they will acquire larger momentum. It becomes faster and faster. However, it doesn't happen inside the wire. It's because they are making collision with another charged particles inside the wire. Because of that, that is a kind of resistance. Because of that, the flow of charge is not accelerating. Instead, it reaches a certain value called the drift velocity. So the current flows in a uniform way. That means applied electric field will contribute to the acceleration of charge, but that kinetic energy is lost and redistributed to the other charged particle to make a kind of vibration. That means that is the Joule heating. Because of that internal energy, the temperature of wire increases when current flows, unless it has a zero resistance. For example, at the absolute temperature 0, it reaches the 0 resistance, then temperature doesn't increase. So there is a proportionality. Current density is proportional to the external electric field. These two are mutually reciprocal. Sometimes we need this, sometimes we need this, but actually they mean the same thing in a different way. So this one, rho is called the resistivity, and sigma is called conductivity. And using this simple relation, we can find the formula that we learned in middle school. I remember, I don't know whether you learned in middle school or not. I learned it in middle school. And we use this to evaluate the resistance of a resistor depending on the length and cross-sectional area. A unit of resistance is called ohm, and we write in this way, and that is identical to volt per ampere. And let me pass this problem, but because most of everything is given in here, and the context of this problem is that we learned in middle school, but in here we need to evaluate the integral that is a trivial integral. So I hope you can follow all of the detail of the calculation in here. Again, just like a reduced mass of a two-body system, the resistance of two connection, this parallel connection is this. I have made use of the superposition principle in here. All right, 11. Charge carriers of each charge can move along the external electric field due to the potential V. We assume that Q is a positive. Electrostatic potential Q due to the external electric field decreases as Q flows parallel to electric field. I think I don't have to explain in detail. This is written, everything is written in here. This formula is also very, very important. Power consumed by a resistor, power, IV, is charge multiplied by potential divided by time. So this is a current IV, and V equals IR is Ohm's law. The potential difference between the two terminals of a resistor is V equals IR. Using this formula, this power can be expressed in three ways, and you have to remember the SI units for the power. Okay,